All right, this will be the final of the 4 Q&A sessions. Terence Witt will be the person receiving the questions. They will be asked in order by Howard Bloom, David Noel, and Lingjun Wang. Terry, do you want a minute or so to just recap Null cosmology?
Sure. I will try to do it quick. It's a big tapestry. But basically, it's a quiescent universe, but then they're a quantified quiescent universe. So if you're going to make the bold statement that the universe is not expanding, then you got some explaining to do. Average universal age, redshift, microwaves, and a number of things. If you'd like to divorce all of the galactic properties away from this, then you don't have to explain those. But in an integrated cosmology, science should do prediction, it should do falsifiability, and it should do insight. So what null cosmology allows you to do is actually understand why galaxies have the structure and the function that they do. And so it actually provides, it's just same as the atomic theory. You know, you've got this one underlying phenomenon, and you notice that in one underlying phenomenon of atomic theory, look at the breadth of what is explained. So I will entertain any questions on either what I presented in terms of galactic dynamics, the form and function of galaxies. I'll talk about quasars. I'll talk, any of the panelists have any questions about literally any of the cosmological data up there. I'm here.
Okay, Howard Bloom, you're up first.
Well, okay, I have 2 questions that are related. What is the big picture geometry of the cosmos that emerges from null theory? And what is the small picture geometry that explains particles?
Okay, so the big picture is flat. It's like a blanket. It's got ripples, but it's generally flat. And this has been measured, and this has been documented that you know, like everyone's been talking about the omega closed, or is it open? Is it all going to end in tears, or is it going to end in a party? But generally, to the extent that we've been able to measure it, it is flat, and that's consistent with null cosmology. You've got this, imagine you've got an average density that we have measured, and it stretches out to infinity, and that average density produces an average curvature, but what that average curvature doesn't have is a orientation. So just like you throw a blanket on a flat floor, you can look at the blanket and you can see you've got an average curvature here. But that doesn't mean the blanket is a big sphere. It's not on the surface of a sphere somewhere. So yeah, that's the now in terms of particles, what null cosmology has derived from the other parts of my theory. And a particle is basically a deflection of space. And multiple deflections. One part of the deflection is electric fields we see. A much smaller part is the gravitational fields we see. So that is, everything's 4-dimensional. And there's an integration. Basically, bottom line is we've got 4 dimensions. And everything we see, if we want to call it kilograms, if we want to call it joules, if we want to call it meters, seconds, everything in this within our 4-dimensional universe can be described in terms of these fundamental units of time and distance, and and so that leads to the derivation of the interior of black holes, which supports their ability to actually eject matter from galactic cores.
Okay, David Noel, do you have a question for Terry?
No, we're pretty much in agreement.
Okay, Lingjun Wang, do you have a question for Terence Witt?
Yeah, to me, Terry's explanation of the cosmic redshift is very similar to tiled light theory, which was well known. So I would not comment on that. What I have a question is about his null theory, null physics. And in your website, I read that the curved space is composed of space. Space is composed of nothing. If the universe is composed of nothing, it sums to nothing. Is that what you said in your website?
Yeah, basically.
And also, yeah. Okay. So is the universe nothing? We are a part of the universe. Am I nothing? Are you nothing?
No, actually, Wang John, it's worse than that. You're less than nothing. Because the universe actually sums to nothing. So you're part of the equation. Now, if you can see the totality of the universe, do you think that, for instance, do you think that the conservation of charge, the conservation of momentum, all these things that are centered around zero, do you think those are all accidents or perhaps a series of coincidences? What we're seeing is we're part of this big equation that adds up to zero. And as a physics prof, you know all differential equations add up to zero. But my question is, so even if you've got a quiescent universe, and you do, why is there a universe out there instead of just nothing? So sure, you can argue that there was no Big Bang, there's no beginning, but the reality is you still got some explaining to do because we got trillions of galaxies that are trillions of stars that are visible in the observable universe. Why are they there? How do you get something from nothing? And so then you look at this something and you go, okay, well, look at this. What do we have here? We've got particles. And then we take our really close at it. We see fields. These fields add up, positive and negative fields. And we get really, really close, but we never see any firm boundaries. This is 99.9999% empty, and everything else there is no boundary. So if we have to decide why is the universe there, how could it not be composed of nothing? There's nothing else for it to be composed of.
Well, the neutralization of charge doesn't mean there's nothing.
The neutralization of charge, what do you mean?
You mean the total charge sums to zero. Positive charge and negative charge sum to zero. It doesn't mean there's nothing. There's still something there. You know, neutron doesn't have any charge, but neutron is something.
No, absolutely.
So, yeah, if I owe you $2 million. What I owe and what you owe me summed up is zero. But it doesn't mean there's nothing. If I grab something, grab $200 from your pocket, can you say I grabbed nothing? I guess the ultimate fundamental philosophy here is that you are taking mathematical point as the physical point. Mathematical point doesn't have a size. Its size is zero. But any physical point, any particle will have a finite size. You cannot just ignore that.
Well, the $1 million that you owe me, I'll accept a check.
So we are not debating on cosmology here.
No, let me clarify.
Hold
Yeah,
on,
I know you are.
Hold on, Lyndon. Let him respond.
Let me clarify. You just made a point. You're right. That $1 million that I owe you, the $1 million you owe me, that is not nothing. Those are less than nothing. Those are components of nothing. Okay. So if you look at -1 plus 1, okay, 0 equals -1 plus 1. Say a positron and an electron. Okay, the positron and electron, from one perspective, from inside of the equation, you see all these positive and negative things. You see everything adding up to 0. We do not see the totality. We're just part of the equation. So yes, these are equally real. You're as real as me. You know, I'm as real as this. What I'm saying is the totality, which we're not able to see because we're finite beings, the totality is in fact 0. And because we know that, now we use that fact. We use that fact when we do conservation of charge. We use that fact when we do when matter, the symmetry, the CP symmetry that Howard was talking about. We use those facts. What I'm saying is that's why the universe is the way it is. It has characteristics based on it. But whether you have a Big Bang or not, like the Big Bang problem is you got nothing, and then we got a universe kablooey. We can have a cyclic Big Bang, like Howard would want, but still you've got this relationship. Why is all this stuff here? It's stuff here because it has to be here in the same way that 0 has to have components. And you talk about math and the problem with math and physics, where do you think math comes from? Do you think that just comes from our head? From where does math emerge? It emerges from the universe. We didn't come along and create math. And math isn't here just for us to write equations. Math is the little generalities that already exist in the physical universe.
Yeah, let me just as a layman try to say. I think the point Ling is trying to make is that there is a difference between nothing and zero. Is that correct, Ling?
Well, I try to clarify the difference between nothing and something. I mean, I know you don't agree with the Big Bang theory. I do either. So we agree upon that. But you cannot just dismiss Big Bang theory by saying physics is nothing. If you say that, if it's effective, you can dismiss Big Bang theory by just saying, now physics is nothing. That will also nullify your own theory.
Right.
Is your theory also nothing?
Ling, I think what you're trying to say, it's a semiotic difference in that Terry is saying that there are things and there are counter things that sum to zero, which he called that sum to zero itself. So it seems like there's just a semiotic difference that you two have.
Yeah, I mean you can say
I don't know why you would put the brand Null physics on your own theory. Now, as a friend suggestion, you may consider use a different brand.
All right, Terry.
And we may have more to talk about it, right? Now, we are actually talking about difference in philosophy, which has little relevance to the focus of this debate. We are debating on cosmology, and your Null physics is actually about the philosophy. How do we look at the universe?
Terry,
and actually, if you see, it actually connects the natural philosophy to the cosmology. And so I would ask you, you don't like my interpretation of nothingness. You don't like the idea of you being less than nothing. Then why don't you just tell me, why is the universe unbounded? Why is there conservation of charge? Why is there conservation of momentum? Are these just magical things that just popped up?
No.
Okay, why is there conservation of momentum?
Because that's the result of numerous experiments.
That's what we're measuring. We verified the conservation of momentum. I want to know why momentum is conserved.
Well, that's the way it is. That's nature. We just studied nature.
Okay, so you're going to go with Archimedes. Everything goes back to its natural place now?
Yeah, it's just like you ask why there's a God. Now you ask why there's a nature, why there's a universe. It's just there.
Well, no, what I'm saying is there is actually an answer to these questions, whether you like it or not. And the reason why energy is conserved.
Questions we cannot answer.
Okay.
Yeah, they do.
Well, let me just. It seems to be that just since Ling had mentioned God, that Ling is saying that there are some things that you just have to accept. Where you're saying that you can. I think Ling is objected that you're trying to inject Terry in your ideas that there are reasons, that there are reasons, that it's not. He's approaching science from a more mechanistic. This is how it works. This is what we do. He's thinking that you're trying to, I think, bring in some outside meaning, right? Is that correct, Ling? You don't see meaning in the universe.
What I'm saying is that there are always questions we cannot answer. Say why the proton would have a mass that's 1,840 times heavier than electron. I cannot answer that. That's just a fact that we know. Why there's a nature, why there's a universe, it's just there. I don't know why it's there. It's just there.
Well,
and people asking me, people also asking me, why are you coming to this world? What's your purpose of life? I don't know. When I was in my mom's womb, I don't even know why I should be here. There's so many questions I cannot answer.
Okay.
Yeah.
So let Terry answer yours.
Okay, to start with, I'm telling you what the answers are. You don't like them. You don't like the concept of nothing. Nothing. I've got a book called Zero, The Biography of a Dangerous Idea. Now you can decide, for instance, that you've got these transcendent concepts. Why does the universe exist? It just is. Well, 1,000 years ago, why does the sun come up? It just does. My premise is that there is no question that logic cannot chase down and answer, that there is no limit to logic. Logic is not, it's not limited to what we measure. It can extend beyond. Because regardless of what you measure or you graph, there's always going to be a place that you can't get to. And my contention is that logic can transcend our ability to measure as long as it's consistent and self-consistent. Now, nobody can conceive of infinity. That makes people uncomfortable. But right here, there's infinity. Everybody worries about big infinity and small infinity, but the distance between my two fingers is infinitely divisible. There's infinity everywhere. You can't get away from it. So no, I disagree. I've provided an answer. You don't like it. Logically doesn't mean it's wrong.
Okay, let me hold on, Ling. Howard, do you have another question for Terry?
Yeah, I do. What's your explanation of the conservation of momentum?
Conservation of momentum is a vector, right? So if you've got a bunch of material, just like the positive and negative charge. So if the sum is always 0, and you have all this momentum going around, and that's why if you have, let me get this right, you've got two objects, and they're adding. Well, it's just another form of addition that has to add to 0. That's why momentum is conserved, because if momentum was not conserved, you would have a net difference, and it would basically change the entire sum of the universe.
Well, when you're talking about conservation of momentum, you can talk about a single body, not two bodies colliding. I mean, the symmetry is a very important aspect of your theory. It's a very important aspect of my theory, too. But the big question is why there is something rather than nothing, and why that something tends to be so amazingly symmetrical. So I'm curious about your explanation of because you made a bold statement, and it was a very impressive one, that there has to be an explanation, first of all, for all of these things, that there's always, where there's a question, there's always an answer, and wherever there's a phenomena, there's a question. Even if we don't see it at the moment, we will see it at some point in time. It's a multi-generational process of asking these questions. So, but you specifically said to Dr. Wang that you could explain the conservational momentum, and somehow I didn't understand how two bodies got into the conservational momentum.
Well, that's typical, billiard balls. That's the archetypical example of the conservation of momentum. Okay.
I actually have an explanation why the momentum has to be conserved. That's directly derived from the Newton's second law. Because Newton's second law says that the time derivative of the linear momentum is equal to the force. If the total force, net force is 0, then the momentum is conserved.
Okay, so you're talking about conservation of momentum and colliding bodies, rather than inertia, the conservation of momentum in a single body.
It applies to anything.
Right.
Okay. So Howard, you're talking about Newton's first law then, wasn't that something in motion?
Well, actually, what impressed me in your work is that you talked about space as a bunch of points, a whole mess of points, and every one of those points as a reflection of nothingness. Now, there was an implication in your work that what actually counts, that a point is only a point because of its relationship to other points.
Yes.
Okay, now that's a very relational view of the cosmos. And that bears on something that goes beyond anything that Newton had to say, which is emergent properties. For example, you're 100 trillion cells, but you certainly don't act like a single cell just because you're 100 trillion single cells. There is a Terry Witt, which has produced a fairly vast theory, despite your nature as cells. We've had, ever since Aristotle, Aristotle, in one of his books in 2 pages, laid out a program for science. Said that you could understand absolutely any phenomena by reducing it to what he called its elements. And then he used a weird metaphor. He said, you could understand that individual element if you understood something that Hammurabi had carved on stone steels, laws of human behavior, codes, laws. So he came up with the idea of elementary laws. We take that idea for granted today. We don't see the underlying metaphor of it. And it turns out that when you break a teacup to pieces, you don't understand the teacup. You understand the pieces. And we've been failing for the last 350 years to look at the big pictures that things working together make. And that's why your point about points only having any meaning whatsoever in relationship to other points was so important. It began to get at the emergent properties of things. So does your idea of galaxies. And so the really interesting thing about your theory is not nothingness. It's how things fight their way out of nothingness and come into being no matter what.
Well, it's conserved, though. They don't. Yeah, I get what you're saying about emergent things, but that's a local phenomenon. When you're dealing with the infinities, the stuff that makes everybody run screaming into the woods, now you're talking about a different regime. So the complexity in the universe is ridiculous. If I do this, which I don't want to do because when I lose video, if I slam my hand into the desk, that will reverberate through to David. Now, he's not going to feel it, but nonetheless, there will be this resolution. That's why I was talking about infinity. You've got an atom here. The sun is affecting it, and Andromeda is affecting it. But in science, what you have to do is you have to break down pieces that you throw away the round off, and you try to get to the nitty gritty, right? So if I'm worrying about how this atom works right now, I can't really worry about the gravitational force of the moon on it. I have to just kind of compartmentalize. So you do compartmentalize things to measure things, but overall, it's all one big equation, and we may not like that fact. In fact, when I was 7, I had this dream that was. Now, this makes everybody nervous as soon as you start talking about dreams, but Howard's going to dig this because he's a very, very broad, very, very interested in lots of different things. But in my dream, I literally thought, okay, we had Casper the Ghost back in the day. Looks like many of us are in the same era. And so I'm going, how the hell can Casper the Ghost go through a wall? How can he see stuff, but yet he can pass through a wall? And here's the epiphany I had, and I don't know whether it's 7 or 8. It's like, what if I'm a ghost living in a ghost world? What if I'm just as real as everything else, and that's why this stuff seems real, because realness is a relative thing. So yes, I may not like being part of a big equation that adds up to 0, but the cool thing is everything around me is too. So I'm just as viable, I'm just as real as any of this stuff.
Okay.
But I'm just saying that sooner or later, mathematics, like I said, mathematics is the shadow that reality leaves in our mind. It's this little tiny thing, and I like to say is, why does everybody think calculus works? Do they think calculus works because Newton had a great day? Do they think that you can add up an infinite number of differentials and get an area because there are some axioms, because the Taylor series works? No, calculus works because that's what our universe is. It's a balance between an infinite number of infinitely small things. And calculus is just a shadow of that.
Okay. David Noel, you had passed earlier. Do you have a question, or do you want to pass again?
No, I've got a question for Dan this time.
Me? Okay.
Yeah. All right. Now, looking at it from as an outsider to some extent, you've brought together this group of people who thought obviously a great deal about this question of the Big Bang, the cosmology and everything like that. And you can see that we've got a consensus that at least the universe is not expanding, and 2, that the cosmic redshift is not due to expansion. Now, these are currently opposite the conventional wisdom. So the question is, how long before what the experts you brought together have concluded, and the conventional wisdom acceptance of how long is that going to take, and should we be doing something to accelerate that shift?
Well, you're asking me a question. I'll just briefly say I disagree with Howard. I'm not a big fan of the Big Bang. As a layman, I see many problems with it. I don't want to interfere so much with your question. The reason I'm doing this show is because I disagree with the Big Bang. I tried about 24 people who believed in the Big Bang and the multiverse and some other more quote unquote mainstream theories. They all did not want to appear. I guess they thought it was a declasse kind of argument to even have. They accepted it so much. I hopefully a show like this or anything else you people might appear on will help get people to think a little bit more. I think it's a good thing. I don't, I've got a couple of questions that I'll ask in our final segment before I give you guys a go-to. But I think it's basically just getting it out there. I think that ideas have to be put out there, and sooner or later, just like a great work of art, if Moby Dick had been sitting in an attic for the last 5 years instead of being published, and it was just the ideas and getting them out there is the thing to do. So hopefully that answers your question, David. Ling Jun, do you have another question for Terry Witt?
No.
No?
No.
Okay, so Howard, are you done?
Well, I'm done with the exception of the fact that I think in science, we tend to look at things from the point of view of double negatives. We talk about entropy. So we talk about form as neg entropy. That's ridiculous. What we really need to know is why this incredible impulse, the cosmos, that comes from Terry's nothing. Why this incredible impulse to be something? And why is that something have an impulse to be so amazingly intricate that it makes a Terry Witt, a David Null, a Dan Schneider, and a Ling Jun Wang? And the ideas that we're discussing right now. There is an impulse toward form, as I said, ornateness, flamboyance, even, in this cosmos. And in science, up till today, we have failed to look at it because we've been doing something very valuable. We've been following Aristotle's reductionist paradigm. It's been incredibly valuable, but it's only half of what the universe is all about. And the other half is form, when things come together and make new emergent properties. 135 years ago, two guys sat in a living room in London. They were talking about the fact that for 50 years, it had been known that if you take two gases in two bell jars and put them next to each other, you get twice as much gas. You understand the properties of the elements of the gas. You understand how a gas works. Okay, now warm the gas up, and all you should get is 1 + 1 + 1, a little heat plus twice as much gas. And that's not what happened. If you put these two gases together, and they just look like twice as much gas, and you lit a match, and you stuck it into these two gases, you had an explosion, and you had this weird stuff on your countertop that had a tendency to slide off the countertop. You could put your finger in it and you could feel it, just like matter, normal matter, but your finger would go through it. And it would slide off the surface and onto your pants, and you wouldn't want to stand up for 15 minutes because people would think that you had wet yourself. It was liquid. It was water. Weird stuff. Now, by adding two gases and a little heat, how in the world do you get an explosion and a liquid? That's the puzzle these two guys were looking at. And they came to the conclusion, they tried to just name the phenomena. So one of them called it heterogeneous causation. His name was John Stuart Mill. And the other one, his friend, Henry George Luce, called it emergent properties. And one of those names lasted and one of those names didn't. But they said until the mathematics of science, and they were talking about the mathematics of Newton in 1835, until the mathematics of science can predict emergent properties, it isn't science yet. It's still as primitive as a stone tool. And that was 135 years ago, if my arithmetic is correct. And we still haven't answered their challenge. Our math is still too primitive. We're still grasping too little of the visible universe in front of us every day of our lives.
Okay, so is there a particular question for Terry?
Oh, well, I can
okay,
speak to what he just mentioned. So in terms of the complexity of the universe and the enormous, ridiculous almost complexity of the universe, imagine if you have this big equation that literally has to add up exactly to 0. Okay, so you've got 0 over there, and now say I've got this mouse, and it's been a pretty good prop tonight. So now I have to have a system that is so complex, so imaginably complex, that this mouse can exist, but then all of its antecedents, every single atom, every single particle in here, stretches back through causation into an infinite path. So this mouse is really connected to the rest of the universe in some way. It's connected to particles that interacted with atoms, that interacted with some T-Rex taking a crap 70 million years ago. It's going all the way back. So if you look at every single thing we've got, all of these things have this connectivity. Now imagine you've got that kind of connectivity, but now you need to have it all add up to 0. How much complexity would you need to have an infinite system that literally has this infinite connectivity over time, but have complete stasis? And so yes, so if you're in one part of this system and you kind of like stick your finger and you've got all this interaction, this kind of responses with you, kind of like a butterfly effect or similar, the kind of response the entire system predicts or actually encompasses is just mind-blowing, absolutely mind-blowing. What we see is conservation of energy, conservation of momentum. We see all these little mini micro tools, but what we don't see is literally everything in the universe needs to be in exactly the position it is right now for it to all work. And that's a level of complexity that is, again, lapsing into philosophy now. We're not going to have a computer that can calculate itself or that can predict itself, you know. So there are some real, well, what's really interesting about some of the developments from that 0, that pesky old misunderstood, ignored 0, is you can actually do all sorts of calculations even on beyond the cosmological scale, like in terms of infinities and in terms of infinite distributions of matter. So yeah, there's an enormous amount of complexity, but I would disagree. From my perspective, I don't think the universe is different an hour from now than it was before. I think it seems different, but that water that you're smearing off that counter, I'm going to collect it all in a bottle, and I'm going to go over here with some electrolysis equipment, and I'm going to get my hydrogen and my oxygen back. And that's part of the renewal thing. Now imagine, if you will, the complexity of just that. So you started off with a couple of gases, and how am I going to get the water back into those gases? Well, we collect that, we've got electrolysis, we add energy, and look at what we need just to get water back and forth from a liquid state. So now we're on the universe scale, we've got protons, we've got carbon, we've got silicon, and we need to affect a process, you know, so there needs to be all the mechanisms in place to redo all of this stuff.
Well, this is where the Big Bang comes in handy. The Big Bang gives you a beginning of the universe. The Big Bang, since I was 12 years old, I've been putting everything I've found, whether it's in literature, the arts, the sciences, all on a timeline. And I've been able to put them all on a timeline, an evolutionary timeline, it turns out, because I have a beginning point, a point where the first plasma emerges, the point where the first quarks emerge, the point where those quarks get together in groups of 3 and become protons and neutrons, all the way up to stars, galaxies, dinosaurs, and you and me. All of that I've been putting on a timeline for the last, I can't do the arithmetic, I think it's 50 years, 60 years. It's 60 years, oh my God. Okay, and using a narrative frame to understand these things, using a Darwinian frame to understand these things, using an evolutionary frame, I've been able to see the emergence of greater and greater and greater complexity, and that the challenge is to predict the next levels of complexity. And until we have a math that can do that, we are still dealing with Oldowan stone toolkits, with very, 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 very primitive math. You've done a brilliant job, Terry, of pulling together just about everything in the universe under a mathematical umbrella. But the big question is not, how does everything sum to nothing? The big question is, starting with nothing, how do things go to the things we see today and far, far beyond them, and even stranger, far beyond them with our help?
Okay. Terry, you go answer that.
Yeah, I can answer that. Yes, Well, evolution is a perfect example of a continuing process of growing complexity, whether it's the evolution of ecological evolution. But at the same time, in basically an equilibrium system, you can have some things that just don't work out so good. So for instance, we're going along, everything's great. We've got our little space planes, and I'm going up to spend the weekend in the moon, and then all of a sudden our sun bursts, and all this beautiful, highly complex evolution just becomes so much toast. And in my mind, that just seems so absolutely unfair. Now, our sun's not big enough to nova, but it's still got plenty of left over to take us out if it would like. If it sends that big mega solar flare in the right direction, it'll take us out. And all this wonderful complexity you're talking is gone. One of the travesties I always thought when I look at complexity and all this, the development is the octopus. You look at the octopus, it's an amazing animal. It can change its color. It's smart. It's got an incredibly large brain for its size. It can, I couldn't move 8 arms. I barely can handle 2 arms some of the times. So I look at all that, dead in 2 years. And then, like the Pacific octopus, it goes through this incredible process, boom, so imagine, the feeling you get, like, I can't believe that you'd have this sort of amazing emergent complexity that's, well, unfortunately, the universe doesn't give a shit whether we want everything to keep moving along, because it will just, not capriciously, it's even worse than that, it just doesn't care. All of a sudden, a huge amount of emergent complexity that will occur in biospheres or whatever else is just blue, and that's the counter. That's the reason why the entire universe is not marching on some amazing trip to increase complexity. We have local increases in complexity, local emergences that someone's waiting around to finish that.
Okay. Well, Terry, I disagree with that. And because, look, you're a brilliant articulator. You're absolutely terrific. You're the star of this episode that we're doing tonight. But the fact is that there is a growth in complexity. We see that in the evolution of life on this particular planet. We even see it in the evolution of stars. The first generation stars are composed of only 3 elements because the universe has only churned out 3 elements in the beginning. And those 3 elements are hydrogen, helium, and lithium. The next generation of stars, when those stars begin to die, they begin to form, to crunch in their hearts through their death, through their agonizing, torturous death. They begin to crunch together 89 new forms of atomic nuclei. So nature is doing, let me just finish. Nature is doing something incredibly cruel, incredibly vicious. She invented death, she invented torment, she invented pain. But she also has a progressive creativity that just keeps moving forward.
All right, let's end this segment here because we're getting off into philosophy and
well, no, it's not philosophy. We're still talking about physics, Dan. Okay, but you see, what assumed that the first stars produce these things. So you're supporting your Big Bang by assuming the Big Bang. No, there were no first stars because you can't make a star out of lithium, helium, and hydrogen. It doesn't have enough density. We've got massive amounts. You need, and that's one of the temporally things, that you need stardust to make stars. And that's another thing the Big Bang has tried to work its way around, saying, oh, we have these really great stars. Man, they could just form out of hydrogen. No, that's not enough density to make a star. In the contemporary universe, you won't find any stars like that, and it's not because there's all these other cool elements. You will find huge, huge clouds of helium, huge clouds of hydrogen, clouds that are 100 times the size of our solar system. They don't condense. They can't. They're too thin, and that's why you couldn't have first stars. So you're supporting your emergence by assuming your emergence to start with.
Okay, let's end it there. Let's end this segment, and this is the final Q&A segment. When we get back, we're going to wrap up this episode. Each of the 4, and I will ask a few questions, and we'll do that in just a moment. I want to wrap up this episode, this show, with 3 brief questions that I'll give each of the 4 men a chance to. Then I will give each of them sum up their ideas and anything else that's left over from the debate. David Noel had asked me earlier about the show, and I should say that I did try to get a big banger and a multiverse proponent on the show. The most famous of them was a Max Tegmark, and there were other people like Alan Guth that I did also query, and they wanted nothing to do with the show. My first question. Let me just go backwards, and I'll pick up on what Howard Bloom ended the segment with. I'm the layman here, so I'm going to ask Howard, and then I'll ask the three others to comment on Howard's answer. For complexity, I thought to have increasing complexity, you need an open system. As a layman, if you are saying the universe is getting increasingly complex, does not that mean that we need an open system, and does that mean that you're a closet multiverser?
The idea of an open system and a closed system comes from the concept of entropy, and it's an attempt to save a system that's based on a model from the 1800s, the 19th century, a model based on the steam engine. Entropy is a ridiculous, go into an entire other show about entropy and why it's a ridiculous idea. So it's time to discard the idea of closed systems and open systems altogether. They're useless in this particular universe. So without those, I'm not quite sure what the question is. Do you want to rephrase it?
Well, no, basically you've answered it. You don't believe in entropy. David Noel, do you have a comment on Howard Bloom's belief on entropy?
I don't see it being a question of open or closed at all. If the universe is infinite, it's neither open nor closed. That doesn't have any meaning. As to entropy, the old idea that the universe is running down and the heat death of the universe is coming up just really doesn't correlate with reality or our increasingly complex ideas of how the universe runs.
Okay.
That's it.
Ling Jun Wang, do you have a comment on Howard Bloom's idea of increasing complexity and entropy?
Well, these are two different questions. First, I don't think the universe is getting any more complex than it used to be. It's just as complex as it was yesterday and as it was billions of years ago. That's what I believe. As to the entropy, it's a concept of thermodynamics. If we use it for a valid thermodynamic ensemble, it's valid. But you cannot push that concept indefinitely to any other systems. Basically, the entropy concept is introduced as a different representation of the second law of thermodynamics, which simply says that a system of order will automatically evolve into a system with less order. And that's what basically it says. However, there are systems and processes in the nature that does go from random to order. For instance, the life is a process. Life process is a whole process of getting the random, irregular stuff to a highly ordered system. That's a human being. Now, how does a life come out? It comes from an egg of a woman. Originally, it's very primitive. You can say very random existence of the state. But gradually, that those material will evolve into egg, and then be evolved further into embryo and to human being, and then to politician or cosmologists, and they can fight in the Congress. It's a very highly ordered process. So this process cannot be explained by the second law of thermodynamics. So philosophically, I do agree that the concept of entropy cannot be pushed indefinitely as a general law of the universe.
Okay, Terry Witt, your comment?
Well, the short answer is entropy only applies which to the extent it can be interpreted to a closed system. And the universe is certainly not a closed system, and Earth isn't a closed system. So in terms of that, and I already kind of spoke to the increasing or decreasing complexity. So yeah, that's my comment on it. You know, it's great for a steam engine as long as you've got them in a sealed hermetic chamber, but for a universe, it's kind of like running around and playing with your dad's gun.
Okay. My second question was based on something Ling Jung Wang said earlier, and he had basically brought up what I would consider a more philosophic point, in that there are just things in the universe that would fall under the heading of just because answers, in that this is there. We are scientists. We are not there to get meaning. We are there to find out the mechanism to it. Thinking of that, and we were talking about mathematics. To me, I think as a layman, mathematics is not a hard thing. I've read people who think that there could be whole universes that are just mathematical equations, which seems utterly silly to me. To me, mathematics is human mind making metaphor, using a metaphor for the cosmos. I wondered, and I had asked this in another show. Do you believe that if there were an alien intelligence, whether it's artificial intelligence that we create or something that grew up biologically elsewhere, that there could be an alien mathematics that could look at the universe and see things differently than we do? Ling, do you have any comment? Do you think that mathematics is human based? Could there be other than a human based sort of mathematics?
No, I don't think mathematics is human based. It's a natural law.
Okay.
All the physics laws must be quantitative. It cannot just merely a gut feeling or a big picture.
Okay.
It's not enough. You can get some inspiration from it, but in order for you to get a mature theory, you got to have a quantitative analysis and equations or formulas. Okay, that's part of the answer. The other answer is there any other aliens in the universe that would have different math? Well, I don't think so. Why? If you look back to the past, thousands of years ago, when the mankind was isolated by the ocean. So to Asians, the Americans are just like aliens. There's no cultural communication. And Europeans and Africans, they are all isolated. They are going to study the nature and find their laws. Will they find the different laws of the nature? No. They'll come to the same conclusion.
Okay.
Like a Pythagorean theorem was also discovered in China.
Well, can I throw in a quick answer?
Yeah,
If they have
This is
aliens elsewhere
interesting.
in the universe,
Okay.
they will have the same description of the nature.
Okay. So
There was an alien on this planet using a different form of math.
Okay.
The year was approximately 1600, and he was trying to figure out the motions of the planets. And he did not use equations, and he did not use the kinds of quantitative stuff that we use today. He used pictures. He used geometry. That was the only math he had. His name was Kepler. And the laws of the planetary motion that we know today that have been quantified and turned into algebra, those are not Kepler's laws. That is an algebraic interpretation of Kepler's laws. Kepler's laws were done with no algebra, no formulas whatsoever. So this supports you, Ling. It supports you in saying that no matter which language of math you choose, even if it's an alien language, you'll arrive at the same conclusions. But it also controverts you to a small extent, because it says that you can understand things with pictures. That pictures are another way of doing math.
Okay. So David Null.
Could I say something?
Yeah, go
then?
ahead. Go ahead.
Okay. First, geometry is a math. Okay. Secondly, Kepler's laws are described by accurate mathematics. The first law says that all the orbit of planets are ellipses with the sun at one of the two foci. The second Kepler's law says that the radial vector for the sweep equal area in the equal time. That's a very, very accurate mathematical theory. The third law is called the harmonic law, which says that the period of the orbit of the planet squared would be proportional to the radius or semi-major cube. So these are very, very accurate mathematics.
Right, but Ling, if you look in the books of Kepler's books, which are filled with pictures, he made lots of them.
I know
You won't,
with the big pictures, but
you-
it does not say that
but
Kepler's
you
law
won't,
is mathematically
hang on,
accurate.
I'm not saying that algebra, I mean, that geometry is not mathematical, it is, but it's a different language. And you won't find any of the equations that we're accustomed to seeing as Kepler's laws anywhere in those books. Those came along when the mathematical language changed and became formulaic. And even though
That depends on what book you are reading.
No, Kepler's books, all of them.
No,
Kepler's whole body of
Kepler's
work.
laws are well described in physics books. And you are saying
but
that
not in Kepler's
he
books.
used any mathematics.
Right.
He used a lot of mathematics.
Yes, he used geometry.
Okay, Ling, Jun, and Hao, David, do you believe that mathematics is universal throughout the cosmos, or could an alien have a different, mathematical approach to the universe?
Well, I think the underlying structure is universal. It must be the same, even though you get local developments which are look at it differently, like in the wave and the particle theory of light. They were really just using different aspects of mathematics to look at the same problem. And nowadays we've more or less concluded that although they appear to be in contrast, they actually come together quite well, and you can have both mathematical descriptions, if it got to that, which appear opposing, but in fact must be reflecting the underlying nature of the universe.
Okay, Terry, your opinion, is mathematics universal?
No, I don't think the form of it. I agree with David and Howard. I think the underlying structure is going to be the same. But Howard had a beautiful example of how it can appear completely different. So even though there might be a law of cosines that's universal, or a pi that's universal, or algebra that's universal, the rules, nowhere does it say the rules with which we construct algebra are really the only ones. And that's kind of like the completeness proof that you really can't do. So if some Klingon came up, and I actually got schooled on Klingon today because my nephew was thinking about getting a Klingon tattoo, in the written language. So if you look at this, and if some alien's going to show us his mathematical calculation, we may not understand any of the symbols. They will probably, if we keep talking about the Big Bang, though, they'll probably just eradicate us. Because I'm embarrassed, if some alien pulls up into orbit and we start talking about 13 billion years ago, all this stuff really happened. It's like, okay, no intelligent life here, let's just nuke the planet. So I'm really concerned that in terms of that earlier question of how long is the Big Bang paradigm going to keep going, and I'm pretty sure, despite what David says, I'm pretty sure Howard's still in that camp. I'm getting the feeling anyway. So
Okay.
if it needs to stop going before the first guys show up. I'm just saying, just as a planetary safety issue.
Okay, my third and final question before we wrap up and have you each give a final closing statement. It seems to me as a layman that one of the things that's very troubling in the last quarter century or so is the idea of dark matter. And for my question was regarding dark matter, and I think that the idea of dark matter as a layman came up with the idea that stars at the edge of a galaxy are rotating quicker than they seem to be, and the idea that there'd have to be more mass there to account for how they rotate as quickly as they do. I read in, I think it was Discover magazine, about a fellow who has an idea called modified Newtonian dynamics, MOND, and I've always thought that dark matter was a case of special pleading. Do you think in this modified Newtonian dynamics theory, the proponent was saying that gravity is not scalar, that at different distances, gravity may act in different ways than we know of, rather than being universal and acting in all ways at all times at all powers. So is gravity scalar? Is it uniform at all distances, or do you think that we may discover in the future that gravity may not be? And if so, that would, I think, be the death blow to dark matter. Howard Bloom, let's go alphabetically.
Well,
Gravity.
I'm not really expert in this matter at all.
Okay.
But I think that you're absolutely right that the problem may not be in the matter in galaxies. The problem may be in our Newtonian math and its limitations.
Okay, David Noel, your comment?
Well, this is a thing which is just recently dropped out, and if you look on the website under the cosmic smog model, you'll find out that when you examine the formation of solar systems, it becomes clear that between the stars there's far more matter than is normally assumed, because it's very hard to detect from this light. And it looks as though this stuff that's left between the stars is in fact the dark matter which is needed to balance the mathematical equations. And interestingly enough, it's also the source of the cosmic background radiation. Now, that's a huge topic, so I won't expand it further, just to say it looks as though we may have the answer to both those topics there.
Okay.
Thank you.
Ling Jun, how about gravity?
Yeah, you were asking about the dark matter, right?
Does gravity work? Is gravity uniform throughout the cosmos?
These are different questions. I'm going to answer both. First, about the dark matter. Now, there are dozen different models of the Big Bang theory. However, they all have to rely on a single most important parameter, which is called the mass density parameter, omega. Now, all the models have to rely on the omega to be almost exactly equal to 1, which means they all predict a mass density that's very close to the critical mass density. How much is it? It's 5 times 10 to negative 30 grams per cubic centimeter. Now, the observed mass by the astronomers and astrophysicists is only 1/33rd of what they predicted. Namely, the observed mass is merely 3% of what Big Bang theorists need. So that's a great blunder. Suppose you have only $3 in your pocket, and I'm a fortune teller. You want me to calculate how much money you have it. Now, my prediction is you have $100 in your pocket. So we're off by $97. You would say your calculation is wrong, wouldn't you? But I can solve that problem politically. I would say that $97 is a dark money. And that's what the Big Bang theorists are doing. They simply claim that the 97% of the missing mass to be dark matter, or dark energy. The truth is, all the dark matters have been observed and measured by astrophysicists since the 1950s, which the mass that they report included the brilliant, the light-emitting objects like stars, and also dark matters like planets, meteorites, dusts, ions, electrons, and you name it. So the Big Bang dark matter is just a political measure to solve their theoretical problem. And the taxpayer have to foot the bill for the big science project looking for dark matter and dark energy. And they found nothing.
Okay.
That's the dark matter issue. It's a very, very serious theoretical failure, one of the most important fundamental problems of Big Bang theories. All right. The second issue is the deviation of the gravitational law from Newtonian theory. Now let me share you with this. All the space scientists, no matter if you are American or Chinese or Russian, they use Newtonian theory to do the research, to use it in their daily calculations, to calculate the orbits of satellites and anything, to the accuracy that we can predict the position of a planet or a satellite 3 years in advance with the accuracy of less than 1 arcsecond. And that's amazing accuracy. There's no solid experiments that will show that the gravitational force deviates from Newtonian prediction, from Newtonian theory. That's my answer.
Okay, Terry Witt, is gravity universally constant, or is it scalar? What is your reply?
It's absolutely universally constant, and the idea that there was this non-Newtonian thing going around started when they first measured galactic disk rotation, and they see this weird flat profile. Because if you look at our solar system, Mercury is blasting around the sun 30 days or so. We're creeping along. Pluto's moving about. It takes about 270-ish years, I think, to orbit. But the galaxy's disk has this flat rotation profile that's baffled everyone, to the point where they've gone pretty much hysterical to say, oh, well, Newton was wrong. Well, don't mess with my buddy Newton. He was the last one that seemed to have things figured out, okay? So the reason why gravity is universal, and as good Dr. Wang said, is extremely accurately Newtonian, but as you go into greater and greater distances, just because you got 600 light years out there, the force decreases as 1 over r squared. That's a dimensional relationship between force and space. So you can't go like 2,000 or 3,000 light years and say, oh, well, gravity is different now. No, that is merely a gross misinterpretation and misunderstanding of how things are working. But what's interesting is I've got this quantified information that I've carefully hidden inside of a book where no one can find it. It will actually calculate what these rotation profiles are, and it will actually calculate exactly how much dark matter is out there. Dark matter is not non-baryonic matter. By that I mean it's the same as this stuff, but we don't see it. We don't see it because the stuff we see up in the sky is on fire. That's fusion. We're seeing it. If you look at a big cloud of molecular hydrogen that's not lit up by anything, it's virtually invisible. And so yes, 97% of the universe we don't see. But imagine what would happen is if 50% of the universe was on fire having fusion. It'd be ludicrous. No, you need all that other material as a huge buffer. And you've got, it's kind of like anything, you know, your logs in your fire. What's the most stable fire? It's after you got those embers, they're just burning along. That's like the universe. A very small percentage of it is visible because it's bright. But if you go 1 light year in that direction, you're not going to see something the size of Jupiter.
All right, let me have each of the 4 men give a closing argument or a statement for a minute or two. Just sum up or whatever you want to say. Howard Bloom, you're up first.
Well, I think, Dan, that you've gotten a remarkable group of people together. It's a tribute to you. The 3 of us believe that the universe is constant and unchanging, that it didn't come from a tiny point and expand in the way that some people think it is expanded. I believe in the view of the Big Bang Theory. I believe in an evolutionary picture of the universe. I've written that evolutionary picture of abiotic matter up in an article in Physical Plus, and it helps me. It's true or false, I will not probably know in my lifetime, nor will any of us. But the fact is that seeing the universe in the framework of the Big Bang and being able to put everything on a common timeline shows an evolution of complexity that's absolutely stunning, like the evolution of complexity on this planet, from megamolecules to cells, which itself is an astonishingly and absolutely amazingly, from cells to multicellular animals, from multicellular animals to people philosophizing about the shape of the universe. This is a progressive aspect of the universe that I believe applies to the whole thing from the very beginning. And yes, I believe there was a beginning.
Okay, thank you, Howard. David Noel, a closing statement, argument.
Just picking up on, I agree entirely with what Terry Witt was saying, that the 97% of what, or whatever of dark matter is just stuff that we're not observing because it's not radiating at the visible wavelengths, visible light wavelengths, and to just put together the things that I mentioned about dark matter and the cosmic microwave background radiation. If as I say, the cosmic microwave background radiation comes from this stuff between the stars, which we call dark matter, the cosmic microwave background radiation, it in fact does let us see that all that matter, all of that dark matter, but at a quite different wavelengths to what we're looking at. So that means a total change to the way we look at the CMBR and look out for individual stuff from matter that's slightly above its surroundings because it's large. So there is a key there to both those questions once people go into it. Thanks.
Okay, thank you, David. Ling Jun Wang, if you would have a closing argument or statement.
Yeah, well, thank you, Dan, and all the fellow panelists for the wonderful opportunity today to discuss and debate on one of the most interesting scientific issues that is of wide public interest. But our debate today is not merely about an isolated scientific issue. It is about the future of the science itself. Over the last few decades, science has been interfered and infiltrated by theological and astrological ideas. One of the most fundamental laws, the mass and energy conservation law, was overthrown by the Big Bang cosmologies and replaced with the creationism. And they are telling a story of mathematical genesis, that the enormous mass and energy could be created out of nothing from nowhere. And one of the most fundamental logic and the common sense, the causality, is completely violated. People are told that the consequence can take place before the cause, and the history could go back to the past. The four-dimensional physical space and time is increased to 10 to 11 dimension or even 26 dimension. The physical universe we know, which is everything and anything there is not reduced to merely a topological manifold that can be manipulated at the mathematician's will. Topology creates world. Topology creates the universe, a multi-universe.
Okay, is that
physical science,
okay,
which is supposed to be the most rigorous human knowledge overtaken from experimental study and theoretical studies of the physical world, is now reduced to a mathematical game of speculation and hypothesis. In a small club of Big Bang camp, the more weird and more whimsical and more incredible the idea, the more attention it gets. The taxpayers are footing the bill for their whimsical imagination. And these weird and whimsical ideas of Big Bang theory are preached into the minds of the younger generation through sci-fi, preparing the future labor force for the Big Bang camp and perpetuating the legacy of creationism. It's just simply wrong and must be stopped. We must strive hard to defend the science from the interference and the monopolization by theology and methodology, and pull the wagon of theoretical physics back to the scientific track for the dignity and the honor of physics and for the welfare of our posterity. Physics needs nothing less than a new renaissance. Thank you.
Okay, thank you, Ling Jung. When the big bangers come knocking on the door, I want you on my side. Terry Witt,
Well, I'm armed.
Okay, Terry Witt, you have the final.
I don't know whether he's armed right now or maybe at home.
First, I have a handgun carrying the permit.
Okay, well, he might be armed right now, so we'll be careful. Well, first off, I want to thank everybody. This has been very fun. It's been lively. David, it was great meeting you. Howard, it was great meeting you. And Ling Jun, it was great meeting you. I want to mention a couple things. Ling Jun, as a working academic, I am very impressed at your bravery in taking on and putting your foot down for science. I'm very impressed with your bravery, and so I had to throw that out there because I've had lots of dealings with academics, and I've had several of them agree with me, but wouldn't dream of putting it in print or going on a debate like this. So I applaud you. And in terms of Dan's question about how long the Big Bang is going to last, well, we spent 3 hours, and Howard still believes in the Big Bang. So if you calculate, okay, less than one whole person every 3 hours, then we got a lot of work ahead of us. But ultimately, I kind of concur with Dr. Wang that we've got a problem in the country where science is becoming less and less like science. Falsifiability, stuff like that is now viewed as naive. We're messing with Newton laws just to make our curve fit. That, I'd say, well, that has to stop, but how are we going to stop it? One of the issues with, we're battling away, but there are a lot of monkeys on this rock that don't care about what we're talking about. And it's somewhere down below, I don't know, national tiddlywinks competition and other things. And we need to somehow get the kids engaged, and we need a debate. A debate is so much more interesting than this mindless narration of, and then back in the day, this and this and this happened. The debates are fun. Let's look at the underlying data. And so right now, cosmology is a religion. A lot of aspects of what should be physics has become religion. Dr. Wang would think that my summation to zero might be bordering on the religious or the philosophical, but I've got the logic to back it up. So I hope that we can move forward. But one of the problems I see is the Big Bang has been as wrong as lug nuts on a birthday cake for 100 years. There's no consequence for it being wrong. When an engineer is wrong, a plane crashes or a train goes off the track. The problem is we can be wrong for the next 100 years. There's no, other than the gradual degradation of science itself, there's no penalty for being wrong on cosmology, and that's one of the problems. So I have no idea how to fix it. I expended incredible resources trying to. I've got a copy of my book in every library in the United States. I've pushed as hard as I can push, but if the other people are not going to open up the book, and as today they refuse to discuss issues, and they think the Big Bang is the same as the heliocentric universe, that is, it is a known fact. Everybody knows that, and they also are completely ignorant of the fact that that's the way history has gone. In 1915, everyone knew that there was only one galaxy. They were utterly convinced. And that was 100 years ago. The celebration of, yeah, one galaxy. Ooh, what are those little smudges I'm seeing up there? Well, right now we've got the Big Bang. That now, hundreds of years later, we can be wrong about stuff that's a lot farther away. We need to integrate. We need to, instead of just measuring stuff, and I'm a fan of science, but we need to measure stuff, and we need to do logic too. And whether we're going to do that or not, who knows?
Well, thank you, Terry.
Well, thank you, Terry, for your encouragement. fighting an uphill battle has never been easy.
Yeah.
But somebody got to say, got to cry, I do not see emperor's new clothes.
Okay. All right.
And it's just simply wrong to spend the taxpayers' money for your whimsical ideas and to cover your mistake. It's even more wrong to preach those whimsical ideas into the young minds of elementary school students.
Well,
And
what I was
high
going to
school
do,
students, where they're only in the teenagers, not knowing nothing, no logical thinking and no mathematical analysis capability. It's just simply wrong.
Okay.
I was actually going to sue the NSF, nationally and federal court, for putting a moratorium on non-Big Bang research. I thought at least maybe with a big fat lawsuit, it would get some people's attention. And then I wanted to put the Big Bangers on the witness stand and say why is this a fact now? But my lawyer's talked me out of that.
Okay. Let's
They
end.
come out and join the public debate.
Okay.
Oh, can I say one more thing, Dan?
Yeah. Go ahead. Go ahead. Final
more thing.
statement.
So when I was promoting my book, Non-Big Bang, I contacted PR firms, various PR firms. I contacted the same PR firm that defended big tobacco against all the lung cancer that they'd caused. Okay, so they're based out of Miami. I don't remember their name, but I went in there and I said, here's the situation. I want to get this book out here. I want to get podcasts. They looked at it for approximately 3 months. Well, actually 3 weeks, excuse me. They said, we can't help you. We can defend big tobacco against all the issues there, but we can, going up against this current science dogma, there's nothing we can do.
All right.
Consider
Then allow me to just mention Stephen Hawking.
Yeah.
Stephen Hawking is a star of black holes. He made a fame and a fortune by the research in black holes. After decades, he admitted mistake once, 10 years ago. Now this year or last year, he admitted the mistake again. He said the black hole is the biggest blunder of his life. And he also announced that Einstein's relativity is incompatible with the quantum theory. Now, how do you make that?
Okay. Well,
The Big Bang can follow the Stephen Hawking for decades.
Yeah.
And now he's announcing that the black hole does not exist.
Okay, Ling.
Why should the taxpayers follow them, foot in the bill, and to do whatever they talk about it? Where is the judgment of the physics community?
Well, he just joined Einstein. Einstein was a crackpot the last 30 years of his life.
Let's end it there. I want to thank all four of you for your lively and energetic debate. That's Howard Bloom, David Noah, Lingjun Wang, and Terence Witt. You can look under this video. You will find links to their websites to find more about their ideas and their writings. Next week, I will be having 3 film critics talking about why film criticism sucks, especially in the 21st century. So we'll be switching gears. Again, thanks to all 4 of you, and hopefully people will enjoy and learn something from this debate.